All yours, Richard.
Okay, thank you, Victor. I'm happy to introduce Irvin Lenzi to our group for his presentation today. I first came across Irvin when I found his book, Fractional Differential Equations in Anomalous Diffusion, which was published by Cambridge University Press in 2018. And I almost read it cover to cover, or at least looked at every page, because it just had all kinds of insight and interesting results that were congruent with some of the things that I was doing with diffusion and NMR. I should also point out, given our study group, that his work with his co-author Luis Evangelista is being extended, and they have a new book, which is Anomalous Diffusion and Relaxation. I mean, give me a break. I mean, how can you be closer to who we are and not be a member of this group? Well, I'm so happy that he can join us today and tell us more about his work. If you want to find out his complete portfolio on Google Scholar, he has several hundred listings. His H-index is 38, and he has almost 5,000 citations. He is currently an associate professor at the University of Ponta Grossa in Brazil, which is somewhere near Brazil. And I'm at Rio de Janeiro, and I hope to visit there someday. He got his PhD at the Brazilian Center for Research in Physics in 2002. He's a youngster. And my understanding is that that institute is basically the MIT of Brazil and educates physicists for all of South America. For example, he has his second most highly cited paper in Google Scholar is a Frontiers in Physics paper titled The Role of Fractional Time-Dependent Operators in Anomalous Diffusion. In that paper, he looks at the Caputo Fabrizio, the Riemann Louisville, the Antagaga Bolanu derivatives, which are non-singular kernels. And he describes them in a CTRW context. He shows that the waiting time distributions are not just power law, but exponential and stretched exponentials. And he's able to then make predictions on the mean squared displacement variations that changes from linear with time to both sub and super diffusive. So he clearly has been working, plowing the same field that we are, at least using the same tools and forging new tools for that. His research interests include complex systems and stochastic processes using ODEs and FDEs, with applications to boundary value problems in liquid crystal systems in MRI. He's a co-author with me on my special issue paper for mathematics, and also impedance spectroscopy, which he'll talk about today. These interests the interest in applying diffusion as we do it in MRI, we sometimes feel like we're pioneers in trying to apply things here, but the applications in fields like viscoelasticity, dielectric theory, and impedance spectroscopy goes back over 50 years. If you don't believe me, I mean, nobody believes me, but if you do believe Oldham and Spanner, go back and look at their 1974 book. It's the last chapter, is impedance spectroscopy. Anyway, today Irvin's going to discuss features of fractional derivatives and how they naturally encode chemical and physical processes, both for impedance spectroscopy and for diffusion, but particularly the diffusion at the electrode interface is where the fractional derivatives become very, very useful. Okay, so enough babbling. So please join with me in welcoming Irvin to our anomalous relaxation and diffusion study group today. As always, you can use the chat space to enter questions and comments during the seminar, and feel free to participate in the online discussions after the presentation. And always remember that this event is being recorded. Okay, back to you, Victor.
Okay.
Or on to you, Irvin.
Okay, thank you for the invitation. Thank you for the opportunity. Thanks for all to this invitation and the opportunity. I will present my talk, and may I share you my screen? Let me share my screen here. Okay. It's possible to see my screen. Okay, let me.
I can
Yes,
see
we
it.
can see it.
Okay, let me just a minute, because my computer is slow. Oops. Okay, and my talk today is about the fractional time derivatives. Okay, fractional derivatives, in particular the fractional time derivatives, the electrical impedance, and the anomalous diffusion. I will present for you some results that I have obtained with Professor Evangelista, Dr. Zola, and other colleagues and co-workers. And I will start my presentation by considering the basic points about the PNP model. After we discuss some points about the experimental data and how the PNP model may be used to describe this experimental data, and in order to observe the disagreement between the model and the experimental data. And after this analysis, we consider extensions based on the fractional calculus. How it's possible to use the fractional calculus to extend the PNP model to describe the experimental data, to capture the behavior of the experimental data. And after we use the fractional calculus to extend the PNP model, we use it to fit the experimental data, to show the agreement between the model and the experimental data. After this analysis, we consider the equivalence between the PNP model and the equivalent circuit. We use the electric conductivity to show how is the diffusion of the ions in the sample when this model is considered to describe the experimental data. We also consider the extension of this PNP model with the fractional calculus for different group of ions and with reaction terms. And we also related this model with different models which has been used to describe or to investigate the experimental data. And after we present a summary. The PNP model, the standard form of the PNP model is based on the following equations. We have the continuity equation, the current density here, and in the current density we have the diffusive term and the drift term, where the potential is given by the Poisson equation here, and we have to solve these equations for the positive and the negative ions. And to solve these equations, we need some conditions for the potentials and for the ions. And these conditions are the boundary conditions. For example, here we have a typical situation, so typical experimental situation. We have an electrode, we have the surface of the electrode, we have the boundary conditions we have the boundary conditions, and we have the conditions now of the potential. The boundary conditions, typical boundary conditions used in these models are the perfect blocking, Chang-Chaffee, and the adsorption-desorption. For the boundary condition, we have no flux at the surface, and the others we consider some flux. In this case, I have the process. We have to consider a process on the surface here, and we discuss later on this case. In this sense, if we consider this standard model with these boundary conditions, for example, in the linear approximation, by considering the same diffusion coefficient for the positive and the negative ions, we have the impedance, and the parameter beta is this one, and here we have the device screening. And the behavior in the low frequency limit is this one for the real part, And the imaginary part, we have a capacitive behavior. The behavior in the low frequency limit, it's important because the disagreement between the model and the experimental data is in this region of the frequency. For this reason, it's important to understand how is this agreement between the model and the experimental data. Here, I'm sorry. Here we have typical behaviors for the impedance for the real part. For the imaginary part, we have the capacitive behavior, Nyquist diagram, and the electric conductivity for this case, with the frequency here, here, and here. If we consider the Jean-Schaffer boundary condition in the linear approximation, it's also possible to obtain the impedance for this case. And in the low frequency limit, we have this behavior for the real part, and we have an additional term. And the imaginary part of the impedance, we have an inductive behavior and not a capacitive behavior for this case. We have a different boundary condition and a different behavior for the imaginary part of the impedance. And here we have an additional term related to the surface effects. And if we plot the impedance, we observe two plateaus, the first one and the second one here. For the real part and the imaginary part, we have an inductive behavior and not a capacitive as in the previous case. And the Nyquist diagram, we have this one. We have the presence of two relaxation terms here. And for the electric conductivity, we have this behavior. And the boundary condition for the adsorption-desorption case. For the adsorption-desorption case, we have to consider how is the dynamic on the surface. For we consider, for example, this case. It's a kinetic equation of the first order, and we have the adsorption or sorption term here, and the desorption term here. And we have the sorption rate is this constant, and this constant is related to the sorption process, and the product of this constant with this is intrinsic thickness of the surface. If we consider this boundary condition where this part is given by this equation, it's also possible to solve in the linear approximation, and the results in the low frequency are these ones. We have the real part and the imaginary part. It's interesting to observe that for the imaginary part, we have a capacitive behavior, and this additional term here related to the surface. And for the real part, we have this additional term, this additional term here. And another interesting point about the real part for this case is that are constants. And the real part in this limit does not depend on the frequency. Typical behaviors for the impedance, for the real part, the imaginary part of the impedance, Nyquist diagram, and the electric conductivity. In this table, we have the main results for each boundary conditions in the asymptotic limit of low frequency. And we use this to investigate the experimental data for some samples. Here, the typical equipment used to obtain the experimental data. Here, we have the electrodes, different view, a solar tron, and the complete equipment. We have the computer, the electrodes, the solar tron, and we collect the experimental data. And the sample is put here in the electrode. For example, here we have the experimental data for the milky water, for the brass electrodes, and for the steel electrodes. And our intention now is to use the previous model to describe this experimental data. For example, if you use the standard PNP model with the perfect blocking conditions, we have the agreement in this region of the frequency and in this region of frequency. But in the low frequency, we have a disagreement between the experimental data and the model for this case. And if you consider the other boundary conditions, we have the same result. We have an agreement in part of the frequency, the region of the frequency, and disagreement in another part. And we consider another typical sample, for example, an electrolytic solutions of this substance. And here we have the Nyquist diagram. We have agreement in this region of frequency and the disagreement in the low frequency limit here. And here is the real part and the imaginary part. And the model does not fit the experimental data. And in order to overcome the situations, we try to use the fractional calculus of fractional derivatives to obtain this behavior, because this is the behavior exhibited by the experimental data in the low frequency limit. And this behavior, it was not obtained from the standard approach. If we change the boundary conditions for the perfect to Jean-Jacques or to a distortion, so it's difficult to obtain this behavior, because we have only obtained the capacitive and not this behavior. This behavior is a typical behavior of a constant phase element. And our intention by using the fractional calculus is how it's possible to obtain this behavior by extending or the diffusion equation or the boundary conditions by incorporating the fractional calculus. We start by extending the diffusion equation, and we extending by incorporating fractional time derivative of distributed order here in the sense of Caputo. This extension is interesting in the sense that this diffusion equation has different regimes. In fact, if we consider a simple case, for example, this one, in the absence of external forces, in a free diffusion case, we have this equation. And if you consider this initial condition, we have this mean square displacement for this equation. And this mean square displacement, or the second moment, in this case is the same because of the initial condition and the boundary conditions. We have this behavior for the second moment, one for small times and another for long times. We have different regimes. And here we are illustrating this point. We have different time behaviors for the second moment in this region, and in this region of time we have proportional to time, the behavior of the second moment. We have the point of a crossover. Oops. Another point that is interesting extending this model is the boundary conditions, is to consider instead of usual time derivative as in the distortion case, a fractional one. For example, we consider here a fractional time derivative in the Kaput sense, and we consider here a kernel, and this kernel is in order to consider distributed order or another time if necessary, another time dependency if necessary. And for this case, in the linear approximation, it's also possible to obtain the impedance for this case. And the impedance is this one. This function is this, where f, beta, and kappa are this. Note that this part is related to the diffusion equation, extension of the diffusion equation to the fractional calculus, and this kernel is related to the boundary conditions of the system. And now we use this impedance to fit the experimental data. And here we have, for example, for the brass electrodes, we have the model with the fractional calculus, this red line, and the black line is the experimental data. And here we have the previous model with the perfect boundary, perfect blocking electrodes as the boundary conditions. We have that here, okay, here we have a disagreement, and the disagreement between the model and the experimental data, if we use the fractional calculus, we have an agreement for a suitable choice of the boundary condition, the kernel, for the real part and the imaginary part of the impedance. It's interesting to note that we are using the same parameters to fit the real and the imaginary part of the impedance for each case. The same parameters used to fit the experimental data here are used here. And if you consider these two electrodes, we have the experimental data and for the real and the imaginary part. It's interesting to note that in this case, for the electrical impedance for the liquids, the surface plays an important role. And this point can be observed in this region of frequency because of the surface interaction with the book. Note that we have this behavior, and if here we have a different behavior for the experimental data. And these different behaviors can be described by the fractional calculus. If we consider suitable choices, and if you consider liquid crystals, for example, here we have the liquid crystals, and they use the previous models, the previous model, it's possible to describe the experimental behavior for the real part and for the imaginary part. And here we have a more complex situations with liquid crystals. We have one plateau and the second plateau, and the same parameters you use here are used here for the imaginary part of the impedance. And we have two peaks here related to relaxation times. And an interesting point if it's possible to describe the experimental data, other models are used to describe the experimental data. And the question is, it's possible to relate this fractional model with the other models. And in this sense, we start to investigate our investigation with the equivalent circuits, and we consider a simple case. For example, we have an equivalent circuit, and this part is related to the bulk effects, and this part is related to the surface effects. And the impedance for this case is this one. And to relate it with the impedance obtained from the fractional case, we consider the limit of the low frequency limit. In the low frequency limit, the previous impedance for the fractional case can be approximated to this one. And the impedance related to the equivalent circuit may be approximate for this. And we may relate the real part of the impedance of the fractional mode with the resistance, the resistive element of the circuit, and the surface effects we may relate it with this part. And in this part, it's interesting to observe that we have the kernel of the boundary conditions here. And okay, and if we perform these relations and the element related of the surface effects, we may consider as given by this equation, where we have an association of elements. Here we have a capacitive element, and here we have the kernel. And with a suitable choice for this kernel, it's possible to reproduce this behavior, which is the behavior of the constant phase elements. For example, if you consider this one, we'll have the surface effects is related to this association of impedances, and we have this of the circuit is related to this free impedance in parallel, an association in parallel. And to show that this relation works, we consider we fit the model with the circuit, or in the other sense, we fit the circuit with the model, and we have an agreement in our range of frequency for this case. And we also consider an experimental data here, the model and the circuit. Another interesting point about this PNP model using fractional calculus is on the question is it is possible to obtain more information about the spreading of the ions in the sample. And in order to investigate this question, we consider the electric conductivity and the relation between the electric conductivity and the diffusion coefficient, because the diffusion coefficient may be related with the mean square displacement, as is shown here. We have the electric conductivity, which is related with this, and here we have the diffusion coefficient which is related with the mean square displacement, and this part can be obtained with our model based on the fractional calculus, and we may use this to obtain the time dependence for the mean square displacement for the samples that we are investigating here. And the electric conductivity is this one. We have the real part and the imaginary part of the impedance, surface, and thickness. And if we consider the electric conductivity for these electrolytic solutions, we have the model is the red dashed line, and the experimental data are the black points. And here we have the molecule water, and the model is the black point. Sorry, the model is the red dashed line, and the experimental data is the black point, and we have these asymptotic behaviors in the low frequency, and in this region of frequency we have a plateau. And our intention is to investigate in this region of frequency how is the diffusion, how is the spreading of the ions, and what is promoting this spreading of the ions. And here we have this equation in the region of the low frequency limit, and these constants were obtained with the model based on the fractional calculus. And performing some calculations, it's possible to show that for this case, we have this dependence for the mean square displacement. We have a linear and a polar law. We have an usual and a combination of usual and anomalous diffusion. And it's interesting to note that this power is related to the choice of the boundary conditions. And for the liquid crystals, we have this behavior for the electrical conductivity, the asymptotic behavior for each case. And perform some calculations, we have for the mean square displacement two power laws, this and this one. And the interesting point about this result, as in the previous case, is that this constant here and here, the constant depends on the surface effects and not the bulk effects in this case for this region of frequency. Another extension that it's possible to consider for the PNP model in the context of the fractional calculus is also to consider different group of ions and a reaction term. And this reaction term may be related to combination of the ions, regeneration or annihilation or something like this. And the current density related to different group of ions is this one. And as in the previous case, we have the fractional time derivative, a kernel, the Poisson equation for the group of ions. And if we consider in the linear approximation, it's possible to obtain some equations, and these equations, it's possible to be solved them and obtain the behavior of the impedance for this case. These are only calculations. We have the current used to obtain the impedance. And here we have the behavior of the impedance. And in this part is related to the reaction term, this dashed line. And the solid line is in the absence of reaction term. And here is the dotted for the fractional case. If you consider fractional time derivatives on the boundary conditions. And here is the asymptotic behavior when we have the fractional case for the boundary conditions. We have a different behavior here. And here is in absence of fractional time derivative. We have a capacitive behavior, and the behavior in the low frequency is different. And if we consider an experimental situation, the model fits the experimental data for different group of ions. And another possibility is we related the model with equivalent circuits, and the question is, it's possible to relate it with another models, and we consider, for example, the model proposed by McDonald, and we try to relate the impedances, and we consider the same. We consider the same as in the previous case. We consider the asymptotic limit of the low frequency to relate the models, as is performed here. The kernel with the constants and the results for the impedance in this case, and if it's and after performing this relation, it's possible to fit one model using the other model, and you having the agreement between these models used to describe the electrical impedance. Okay, and in summary, we have analyzed the PNP model by considering fractional calculus. We have a good agreement between the model and the experimental data, and we have shown the relation between the PNP model and the equivalent circuits with constant phase elements and another models. And we have analyzed the ion mobility for the electric conductivity. And in this case, we have shown that in the low frequency limit, the mean square displacement and may inhibit an anomalous diffusion process. And it's important to observe that in this region of frequency, the surface effects have a pronounced effect on the behavior of the impedance, and consequently in the ion mobility in the sample. And thank you, and obrigado. Thank you for the opportunity of presenting my work here.
Evan, thank you so much for the talk and taking time out to join our study group. Thank you. And so normally what happens now is we'll take some questions from our audience and the people joining us. And there's two ways we do this. Sometimes people write their questions into the chat box, which I can read out, or people can just unmute and put on the video as well, and they can just ask the question in person. So Richard had a few questions. So Richard, would you like me to read them, or would you like to reflect on those?
Go ahead and read them. You got them there, I think, right? Mm-hmm.
Yeah, so Richard had a few questions. So the first one was, can the flux in the boundary condition be modeled as a space fractional derivative?
The fractional, and okay, it's consider the fractional space derivative on the boundary conditions. The question about to consider the fractional space derivative, it's possible to consider in my point of view, it's possible to consider the fractional boundary conditions in terms of the special fractional derivatives. And however, we use the fractional time because it's for us was more suitable to solve the equations, and to solve the equations with the fractional boundary conditions in terms of the special fractional derivative. It was very difficult for us, but maybe in the sense of the numerical approach can be possible. I think we did not try to do in this sense because we first use the fractional time derivative, and the agreement with the experimental data was good. For this reason, we use the fractional time derivative. This is the reason that we did not use the fractional spatial derivative. If the fractional time derivative does not work, the next step is try to a fractional spatial derivative for this case.
So you happy with that, Richard? I guess I'll move on to the next question.
Yeah, sounds good to me.
Yeah. So for the mean square displacement, is there a simple way or formula for estimating the crossover frequency?
Okay, is the mean square displacement, and Our question about the mean square displacement is the following point. We, in my opinion, okay, we are consider, for example, water ions in the samples or an electrolytic solutions, and we have a lot of developments by using the standard diffusion or the standard approaches, which in general does not use the fractional calculus. And the question is, okay, and the fractional calculus is essentially related in several situations to an anomalous diffusion. And we think it is possible to, by using our formalism for the impedance, to obtain the mean square displacement for this case. And in the sense that we are try to relate the electrical quantities with another quantities. In this case, we have the diffusion coefficient and the physical chemical parameters. And in this sense, we are using our impedance, which is basically an electric quantity. It is an electric quantity obtained from the fit with the experimental data, and we approximate in this region of the frequency where the standard approach does not work or does not capture the behavior of the experimental data. And using this approximation, we obtain the mean square displacement, because in a different sense of, for example, for example, if we consider in general, we use the distribution or something like this to obtain the mean square displacement. In this case, we does not have explicitly a distribution like in the Brownian motion or something like this, where we have a diffusion equation. We have only the electrical impedance based on a diffusion equation. Explicitly, it does not have a distribution like a Gaussian or extraction. For this case, we consider this procedure to obtain the electrical impedance is not a direct, but an indirect way to obtain the mean square displacement.
Okay, so I'll just follow on from that with another question then. So Richard also asked, what is the difference from the fractional calculus point of view between your model and the McDonald model?
I'm sorry, I did not hear you.
So what is, from a fractional calculus point of view, can you comment on the difference between your model and the McDonald model?
Is the McDonald model. The difference, we are using explicitly the fractional calculus, and in the McDonald model, we have extensions, and we use there are presence of frequency power gamma. However, it's in this, in my opinion, this expression for the impedance, which was proposed by McDonald, I think that it was based on the constant phase elements, is the behavior of the constant phase elements, and observing this behavior of the constant phase elements in the standard PNP model. And I think that he unified these two behaviors in one impedance. I think that in some sense, I don't know if I can say it's an empirical impedance. It's not possible to, I try, but it's not possible to obtain from for example, like this case in the fractional case. I think that he unified the fractional, the constant phase element behavior with the PNP model in one impedance to describe the experimental data, observing the experimental behavior of the several cases. I think that he had studied or analyzed and investigated. I think that is my
This
opinion.
has been one of the problems I see, is that a lot of fractional calculus hides below the surface of some other model, like constant phase approximation or constant phase element. You know, people include an integral kernel in their model, but they don't use the formal apparatus of fractional calculus to generate it. And then, and so that it's sometimes hard to find where it lurks and how to manipulate it. But yeah, interesting. Thank you.
Thank you. Yes,
So
and
we got some, sorry. Yeah, go on, Irvin.
I'm sorry.
You go on. You were going to say something.
Okay,
sorry.
I'm sorry. Okay, in my point of view, the use of fractional calculus is interesting in the sense that, as in the case of the PNP model, you know, which related the physical chemical parameters with the electrical parameters, the extension of the PNP model to fractional calculus has the same idea to relate the parameters of the model, physical, chemical, the bi-screening, diffusion coefficient, constants of the surface with the electrical quantities. The idea is the same, try to this relation. If you use, for example, electrical circuits, these connections, I think that is missing, is not present, because you have the resistance and the capacitive, but it's important to relate this resistance, capacitive, inductive effect with the physical chemical parameters in present
Yeah,
in this.
usually that hides in the conductivity or the permittivity of the sample. But yeah, thank you. I'll let other people have questions. We can talk other times.
So we have a question from David. So David can unmute himself as well and put on his video if he likes, but I'll read his question. His question is also in the chat box. He said, I might have missed this, but you indicated that surface effects influencing the low frequency behavior. Is this supported by some kind of mechanistic / physical explanation interpretation?
Yes, this approach is this approach that I presented for you is a phenomenological approach. And this is good questions, is how to relate it, this behavior with a more fundamental mechanism present in the sample, in the sense, for example, that Hamiltonian, how it's possible to obtain the surface effect for a Hamiltonian system, or something like this, to obtain this behavior for our systems. We have only obtained that in the low frequency we have an anomalous behavior, and this anomalous behavior seems to be related to the surface effects. And if we think in a random walk approach, we have a non-standard random walk approach, because the mean square displacement, it has a nonlinear power law dependence with the time. And in this sense, we may think that the surface promotes an anomalous diffusion with waiting time distributions, if I'm correct, with a long-tailed behavior, because I have power law for the mean square displacement. If we, I think, thinking in a random walk, in a continuous time random walk approach, and that the mean square displacement, a power law in general, is related to waiting time distributions with a long-tailed behavior, to obtain this behavior for the mean square displacement. I was thinking I have to how to obtain this mechanism of the surface from a Hamiltonian for I'm trying, but until now it's a question to me how to obtain these effects for a Hamiltonian or for a more fundamental process, mechanisms in this scenario, in this experimental scenario. It's not easy, this question.
And I think David had another one following on from there, which was in the experimental data he observed, he noticed some low frequency, hang on, there were some oscillations at low frequencies in experimental data, which the solution was not able to capture. Is there an understanding about what causes those oscillations?
Okay, in the presentation, we have a situation with two peaks in the impedance, and these peaks are related to the relaxation times. And for if we have an oscillation like an harmonic function, I don't know if it's possible for an experimental data, an oscillation like a trigonometric function or a cosine or sine or something like this. We have a lot of oscillations. I don't know if it's possible, because each oscillation in general is related to a relaxation time and a process present in the sample. I don't know if it's possible a sample exhibit a lot of oscillations like a function, this one.
Irvin, I maybe didn't come through, but I guess I'm not sure if it's clear. What I was asking is, in that low frequency regime, there seemed to be some sort of little wiggles in the data that were not. I mean, your fractional model definitely captures the sort of the slower, smoother changes of those curves quite nicely, which is impressive. But I guess I kind of wondered, there seemed to be little oscillations that sort of deviate from the model, and those oscillations kind of look different depending on the surface condition that that you were measuring from. And I guess I kind of wondered what those are. Is that some kind of artifact in the measurement, or noise in the measurement, or is that maybe a physical process that's happening that's just not being modeled?
Because in general, my colleagues from the University of Maringá performed some measurements about in the low frequency limit, and it's very difficult to perform some measurements in the low frequency limit because we have this one, we have a lot of oscillations. It's very difficult to measure, and in general, these oscillations are the noises in the experiment, because it's difficult to, how can I say, screen the sample because of the electrical influence of the device or the another thing. But in general, the results that I have observed are like a straight line. Okay, we have one or two oscillations, maybe 3 oscillations, but not this one, like this oscillation. And if these oscillations are present, I don't know if it's possible to describe these oscillations, maybe in terms of an average, but to capture this, I think that is very, if the sample exhibits this, I think that is very difficult to capture this behavior in this sense. It's not easy.
Thank you.
Thank you.
I actually have a question as well. So I do a lot of fitting of data, and sort of like what you do with models. And the thing that sort of strikes me every time I do this is that when we go from the sort of the classical case to the fractional case, it's always the case that you have more parameters in the model, right? And so when you have more parameters in the model, you have this expectation that it's going to fit better because you have more parameters. So then the question then is, I think in your results, and what I always refer to is, okay, it fits better, that's great. But I guess the question I have is, how do you validate the parameters, the model parameters, and how do you know that they're actually given a reasonable range?
Yes, I understand the question, and this is in general a question about this model, not only in the case of the impedance, but in general for the fractional case, because the question is, you have one more parameter to use, or two. In our case, you have more parameter, and you have one or more parameter. But my point is, okay, you may use. The question is, how is the behavior in this region of the frequency? Because we may use another function with a lot of parameters, but the question is the behavior. And the behavior is this one reproduced by the fractional calculus. If we try another function with another parameters, we will not reproduce this behavior. This is my point about the parameters, that it's okay, we have a parameter, but this important is the behavior of the impedance. The behavior is this one. We may try to use, for example, a power law, a series of power laws, okay, a polynomial function, but the behavior is not the behavior of the experimental data, and which can be obtained with a simple change in the formalisms, on the formalism, by using the fractional calculus. The question, okay, I agree. The question is how to obtain the fractional parameter before you perform the calculations. This is the question, in my point.
I mean,
to answer,
that could be a validation question. Is it valid, basically? Yeah.
Yes, this is an important question, but my point is the behavior of the function, because we may consider a lot of parameter in the standard approach, for example, another parameter, but the behavior in this region of frequency is different from the behavior of the experimental data. And we will not reproduce the experimental data because the behavior is different. I think that the question is the behavior, and because the behavior is like a constant phase element. I think that my point is this, but I agree that we have the parameters, and I would like to find them before to perform the calculation. But these parameters are related to the surface, and for example, the diffusion coefficient is fixed. The number of ions is fixed, and the question is the surface parameters. These parameters depend on the equipment used to perform the measure. For example, the electrode. How was prepared the surface of the electrode? And
I mean, the surface of the electrode could be causing all kinds of complications. I mean, these oscillations that David cited, you could have some ions binding and releasing, or forming small complexes near the surface, and each of those might, induce some sort of oscillation. You're right.
Yes, and the fitting parameters are related to the surface, which is very complicated to describe them.
The acid test, Victor, that I've seen with this electrode work is the physical chemists who use the so-called mercury drop electrode. They use for the electrode a drop of mercury, which through surface tension forms a perfect sphere. And then they stick a little wire in it.
Yes, yes.
And this absolutely smooth, absolutely round. And you know what the alphas, and then you fit it with the fractional model and look, and you know what you get? You get exactly 1.0000 for the alpha.
Yes, yes, and the
Take a
surface.
conventional platinum electrode or brass electrode or steel electrode, as he's doing here, you know, then you start seeing slight divergences. But then often you go to a completely non-polarizable electrode where you put carbon black or something, an amorphous surface on the top of these electrodes, and then you need the constant phase element. So there's clearly interesting surface sorption, desorption processes there that perhaps only the fractional diffusion process and fractional relaxation can capture.
Yes, this is the problem. And we have also some maybe some experiments using fractal electrodes or surface like with fractal. It's not
a
easy to
fractal model.
capture this experimental behavior.
Yeah, thank you. It's just something that puzzles me in what I do as well. And sometimes I just wonder. Yeah, I mean, I understand because you have a model, you're basically extending the model, you're basically taking to fractional, but at the end, you are actually having more parameters. So yeah. Yeah, but I guess the thing to do is measure the parameters somehow. Right?
Yes, but it's important to observe that this model is a phenomenological model. There are several points to be answered. To be, for example, this question about the parameters, the surfaces, there are a lot of questions that we need to answer. I have no answer for a lot of questions about this.
Right. All right, thank you, Evan. I think people are hopping off now. I think people have to go sort of hit our time. I just wanted to say thank you again. And we look forward to your future work as well. So